Yeah, so should we have our test on, let's say Thursday? Last test on just a few sections. What do you think? Yeah, I don't have to give a last test, but if I don't, the final build will be heavy. So let's do Thursday. And so this is the honest truth. This is like, I swear to God, kind of truth. And it is that people do really good on the last test. Okay, so that's based on my experience. Exam 3 was supposed to be the hardest, and exam 4, the test on basically the parametric equations, that is I guess the easiest, because historically people have done best on that test comparing to the remaining. And yes, Anna, the final exam is going to replace your low score. Yeah, it does. So if you messed up on, like, let's say test 2, you got say a 20%, or on test 1 you did really bad, your final exam percentage is going to replace that score. So almost anyone has a good chance of getting a B or an A, to be honest. I don't even know why people drop my class. In the end, some end up regretting, because I guess you guys can check my grade distribution. You can, right? So check it. Yeah, so exam 4 is gonna be on, I'll tell you now exactly what sections. Let's see, do I have my syllabus here? I don't. Let me look at my syllabus on my computer. Give me a second. Yeah, so test 2 will be on sections 11, 8, 11, 8, 11, 9, 11, 10, excuse me, 11, 8, 11, 9, 11, 10, 10, 1, 10, 2, and 10, 3. 6 sections. I'll type.
Professor, didn't you say we're coming back to one of the sections?
Yeah, okay, so you know what I'm gonna do? Well, we're gonna hold on to 1110 because I did not fully cover 1110, which really relates to 1111. 1110 and 1111 are almost, I combine those two. So 11.8, 11.9, 10.1, 10.2, and 10.3. Yeah, so 5 sections. It won't be bad. Any questions, guys?
So no 1110?
No 1110 yet. 1110, if I fully cover, well, I will put 1110, at least the McLaurin and the Taylor series part on there, and the applications of it. If I get to cover that, I will put that also on the final. But 1110 will be on the final, okay? And 1111 and 1110, if I cover the rest of 1110, I combine those. Yeah, and I think we're gonna have some time to cover those sections towards the end. But I have today, tomorrow, and Wednesday to cover the polar coordinate system and the next section, which is area in the polar coordinate system. It's a must-know section. All right, so we are talking about the polar coordinate system, which we said is a convenient way to do certain measurements. So again, if you have, if going with distance and angles is convenient, then we choose a polar coordinate system. Okay, you are gonna see exactly why the system is nice in certain situations. Okay, but again, a polar point is addressed by how far it is from the origin or the pole, and the angle that the segment makes with the polar axis. So again, that is the pole. This is the polar axis. Okay, and we saw how to locate these points, which is really same point but with different addresses. And I intentionally went with these examples because I wanted to show you guys that the address to a location in polar coordinate system is not unique. Just give me 1 second. A sudden update. Okay, so the address to a polar point is not unique. Again, we saw that the same location can be addressed in many different ways. All right. Now, next topic in the same section has to do with transforming a rectangular point or a Cartesian point to a polar point or vice versa. So imagine you have a rectangular point xy in the two-dimensional space. Okay, so a point that you became familiar with in, I don't know which grade, 5th grade, 4th grade. Question is, how do we convert that point into a polar point or vice versa? How do you convert or transform a polar point into a Cartesian or a rectangular point? This is called transformation. Between coordinate systems. Again, this is section 10.3, which is also a fairly long section. Yeah, so if you're going to be a math major, you are going to do this a lot. You're going to transform between one system. You probably have heard of, if you're a nerd, you probably heard of the Jacobian. Jose?
Yeah, the determinant, right? And the matrix.
Yeah, I told you, he knows about it already. Yeah, we have many different systems. We have the polar coordinate system, Cartesian system. We have the cylindrical system and spherical system. Cylindrical and spherical are for three-dimensional space. But you can go from one system to another system. Transformation. And this is an extremely easy idea if you know very, very, very basic trigonometry. It sounds fancy, but it is super simple. So let's say this is the XY plane. Okay, and this is the origin. You can again think of that origin as the pole. Okay, here is the pole, here is the polar axis. And the polar axis, of course, coincides with the positive x-axis. Okay, again, your good old x-axis, y-axis, and you can think of that as the polar axis. Who cares? Okay, you could just say this is the origin of xy as well as the polar as well as the pole. All right, so let's say here we have a point, and the Cartesian address to it is x, y, of course. Okay, so if that point is xy, then this distance is, let me do that again. This is, why does that happen? Okay, good. So that's x, and this here is, maybe I can, hold on, let me dash that. You can draw a triangle, a right triangle. Think of the horizontal leg as x and the vertical leg as y. Okay, at the same time, this is the directed distance from O to P, which is we call R, and this is the angle theta. Okay, a very simple relationship between R, theta, x, and y. Simple relationships. We can see that cosine of the angle theta here is equal to adjacent, which is x divided by R. Okay, well, this tells you that x is equal to R cosine of theta. And likewise, sine of theta is the opposite, which is y divided by R. And that tells you that y is R sine theta. And there you have transformation. Your first transformation equations. If you want to go from a polar version of a point, which is R theta, okay, you put R here and theta here, that gives you x, and R sine theta gives you y. So you have xy, which is the Cartesian or the rectangular point, or form, I should say. Okay, so given, so this is to go to transform from R theta to xy. Okay, you want to go from polar to rectangular. I should. So from polar R theta to rectangular. Xy, the transformation rules are x equal to R cosine theta, and y is equal to R sine theta. Okay, so that's our first rule. Very simple, no-brainer, basic right triangle trigonometry here, and that's it. A lot can be done using this simple idea. Before I say the next thing, before we go over xy to R theta, I want you guys to pay attention to these equations. for a second. What do you exactly see? You have two equations. What do these equations remind you of? Something that we
Parametric.
say what?
Parametric.
Parametric. Yes. These are just parametric equations. These are parametric equations. X is a function of, theta. Here, y is a function of theta. We have parametric equations, and we're going to talk about that very soon when we talk about derivatives and stuff. And if you want to go backwards, so here to transform from rectangular xy to polar, which is r theta. There are several ways that you can do this. So you have xy, you have a point like 1, 2, and you want to get r and theta. Well, to get r, just look at that right triangle. Okay, you have a right triangle, r is the hypotenuse. So you can use the Pythagorean relationship, which is r squared equal to x squared plus y squared. Okay, you have your x and y, square them, add them, and that gives you square of r. And then you have to take the square root. When you take the square root, you get a plus or minus. Remember, we said r can be positive or negative. You can choose either one. You could take the plus or the minus, but you have to choose theta according to that. Okay, to find theta, you can, for example, do cosine inverse of x over r. You have cosine theta equal to x over r. You could do cosine inverse of that. You can do sine inverse of that. But to go from directly to go from xy to theta, just do tangent inverse. We know tangent of theta here is y over x. Just use this relationship. This is going to give you theta. Whatever you get for y over x, you do tangent inverse of that, and that should give you theta. Okay, so let's see how these equations or these transformation rules work out or work. We usually go from, we do typically for our examples use these rules. Okay. Oh, by the way, here I should say, of course, x can't equal 0. All right. If x is equal to 0, guys, if x is 0, you know where the point is. If x is 0, the point is somewhere on the y-axis. This is a point where x is 0. That angle is pi over 2, isn't it? If x is 0, we know which angle we are dealing with, either pi over 2 or 3 pi over 2. You know, given that r is positive, this is pi over 2, this is 3 pi over 2.
And I'm sorry, really quick, what did you say in regards to r if it's negative?
Yeah, then you have to choose your theta properly. Okay, we'll see examples in a second. All right, so we're gonna find the rectangular form of the polar point 3 pi over 4. The re's are pi over 4 is theta. You know, honestly, you could just draw this thing if you want. Let's just draw it. If you draw it, it's easier to make sense out of the answer. Or if you draw it, you're less likely to make a mistake, I should say. Okay, so here is the pi over 4 angle. Okay, and we go 3 units in that direction. Okay, so that is the point. All right. One thing we know about this point is that both x and y coordinates are the same for that point, because that's of course the 45-degree angle, right? All right, so very easy. Here x is r, which is 3 times cosine of theta. Theta is pi over 4. That gives you 3 root 2 over 2. Okay, and y is the same thing. R sine theta. 3 sine of pi over 4. And that is also 3 root 2 over 2. Okay, so the rectangular version is, 3 pi over 4. In rectangular form is 3 root 2 over 2, 3 root 2 over 2. Is the location of that point, 3 root 2 over 2. Okay, this is the same point. Polar form. That's the polar form. This is the rectangular form. This is r versus theta. This is x versus y. Okay. Very simple. Yeah. All you have to do is just plug into r cosine theta, r sine theta, and hopefully you know the cosine and sine of that angle. And usually it's a special angle, so you can just look at the unit circle and get the value. Else you have to use a calculator. Okay. Oh, by the way, this is a polar grid. We're gonna be working with this in a little bit. Let me just get rid of it for now. Put it somewhere else. Okay, so next example, let's do one where you have to convert from rectangular to polar. It is 1 for r, and I'm sorry, this is x. X is 1 and y is negative root 3. That is xy. It's a rectangular or Cartesian point, and we want to change it to a polar point. Okay, so first of all, guys, with this particular problem, it is the best if you just locate that point in R2. Okay, for the last example, we don't really need to. All you have to do is just directly substitute your r and theta, get x and y. But here it is better if you draw. And you'll see why in a second. So this is xy. Again, you could think of that as the pole. Think of that as the polar axis. We're going 1 for x and negative root 3. Root 3 is about 1.7. Okay, so that should be somewhere around here. Yeah. Yeah. Okay, so that's the point. All right. And we need two things, guys. We need R. So again, R is this distance. And we need an angle. Okay. We need the angle. The angle could be either, remember, R and theta are not unique, okay? You can do this several ways. You can say this is R, so R is positive, and say this is your angle. That is the angle, okay? So go this much, okay, rotate that much, and then go this much away in that direction from the origin. Or you can go clockwise. If you go clockwise, your theta is negative, and then go in that direction from the pole, your R is positive. Or you can instead go this much, rotate this much, all right, and go in the opposite direction by this much. In that case, R is negative. There are just millions of ways that you can do this problem. Okay, we'll do it both ways. We'll do it both ways. All right. So yeah, so let's set up the problem. Here we know R squared is equal to X squared plus Y squared. That's a relationship between R, X, Y. Plug in. You have R squared equal to 1 squared plus negative of root 3 squared, and that gives us 4. This gives you R equal to positive or negative 2. All right, let's hold on to that, to those values. Also, we have tangent of theta equal to y over x, relation between x, y, and theta. Set this up, you get tangent of theta equal to y here is negative root 3 over 1, or tangent of theta equal to negative of root 3. All right. There are so many different angles that give you guys this tangent. The reference angle, first of all, is pi over 3. Right? Tangent of pi over 3 does give you root 3. Go back to look at your unit circle if you don't know where from. Yeah. So Jose here is saying the range of arctan is from negative pi over 2 to pi over 2. Yes, it is. But you are not restricted, Jose, to restrict your theta in that range. We don't care about the range of tangent inverse. Okay, but let me talk about when this happens. Okay, so tangent of theta equal to negative root 3. It happens in, so this happens in quadrant 2, where tangent is negative. The angle is, does anybody know?
Would it be 7 pi over 4? Or no?
In quadrant 2, tangent is negative root 3 at 2 pi over 3, I believe. Why pi over 4? Guys, at references of pi over 4, tangent is 1.
I know, just the graph tripped me up. I looked at the graph.
Yeah. See, this angle is 60 degrees. okay? It is a 60-degree angle. So it's references of pi over 3, okay? In quadrant 2, so I don't care about that point yet. I just want to know for what angles this is true, okay? Tangent is a negative root 3, is negative in quadrant 2, okay? And the angle would be this angle. That angle is 2 pi over 3. Okay, so maybe I can draw that for you quickly. We're talking about this angle here. Okay, that is 2 pi over 3. And it also happens in quadrant 4 where tangent is also negative with theta equal to 5 pi over 3. Okay, so we're talking about this angle. All right, that's the 5 pi over 3 angle. All right, so let's do this problem in 2 parts. I want to come up with 2 different versions, 2 different addresses for the same point. And if I ask you a question on the test, I will ask you what kind of answer to get. So let's say part A, we are going to assume theta is between 0 and 2 pi. Okay, and R is positive. So we want to get an answer with a positive theta and a positive R. Okay. But we are looking at basically this scenario. Okay, because if you measure this much and go that way, your R is going to be positive. Yeah, so what you do is just go clockwise, counterclockwise. We'll go counterclockwise by 5 pi over 3. Okay, and in that direction, go 3 units. Okay, we go this way by 3 units. If you do that, R is positive 3. Okay, so here the answer is going to be 3. I'm sorry, 2, not 3. It's 2 is what I meant to write. Because we got 2 for R, didn't we? Yes, so go positive 2. Okay, for R and 5 pi over 3 for the angle. Okay, so again, that angle is from 0 to 2 pi and your R is positive. Again, we're going counterclockwise. Okay, I'm not going around 2 revolutions to get there. I'm just going around so that angle is between 0 and 2 pi positive. And in that direction, go 2 units away from the pole.
Professor, would negative 2 pi over 3 give us the same point?
Yes, it does. That would be part B of the
Okay.
problem. Okay, so that answers this question. Okay, for part B, we're going to again assume theta is between 0 and 2 pi, and R is negative. Okay, so we're done with that part. Okay, so we want to choose a negative r, and here is a drawing. So what you do is with a negative r, we have to go this much away from the polar axis to that terminal side, and then go the opposite of that to get a negative r. Okay, so let me extend that segment. Right, so measure counterclockwise. Okay, the terminal side of the angle is of course going to be in quadrant 2. Okay, so again, we know that this thing is, this segment is in quadrant 4. Now, if you want a negative r, then the terminal side of your angle should be in quadrant 2, so that you, when you go the opposite way, you fall in quadrant 4. Okay. So here, since we want r to be less than 0, the terminal side of theta should be in quadrant 2. Okay, so that would be this angle. Okay, the angle whose terminal side is in quadrant 2. So the answer is what you said earlier, -2 for r and 2 pi over 3 for theta. Okay. And that's it. So please go over this example again. Just a review of what we talked about earlier. But these equations, this equation right here, where is it? Tangent of theta equal to y over x has infinitely many solutions. This thing, okay? I took for this example, we took thetas to be between 0 and 2 pi. That's what we typically do. Take thetas between 0 and 2 pi. Okay, very good. So let's talk about polar functions. And I kind of showed you guys this thing, the polar grid. So this is a polar grid. We're going to be using it a lot. The polar grid is not like XY, the XY plane. Okay, the polar grid consists of angles. These are terminal side of angles. Okay, and we have the distance from the pole. So you see these circles? That grid is meant to be there so that you can count, you can correctly count away from the pole. All right, so if you want to locate, let's say pi over 4, 3, we know that this is the pi over 4 angle. Okay, we have to go on this terminal side. Then you go 1, 2, 3 units away from that, and that would be your polar point 3, pi over 4. This is just meant to make graphing in polar coordinate system easier. Okay, but this is the pole. This is the polar axis. You can Google this thing. There are tons of polar grids out there on Google, on the internet that you can get. But now we want to talk about polar functions and polar graphs. Okay, so what we do here is we are going to define a polar function by r equal to some function of theta. Okay, here r is defined as a function of the angle. Okay, this is telling you that input is theta and output is r. How far from the pole? Okay. So for example, let's say for a function r equal to f of theta, we have, say, f of pi over 6 is equal to, let's say, 5. This is telling you that when angle is pi over 6, distance from the pole is 5. Okay. That's why this is a function. Plug in an angle, evaluate, and the function spits out how far the point on graph is away from the pole. Okay, so here is the polar axis. What you do, just go pi over 6. And count 1, 2, 3, 4, 5. Okay, this point is gonna be on the graph of, on your polar graph, basically. Right. Remember how we graph functions in the very, very beginning? We plug points. We're gonna see different polar functions. We can plug points. All right, let me just show you an example with a polar function. Let's say f of theta is cosine of theta. This is a polar function. All right. Yeah, so here we have, if I plug in several points, let's say f of 0, you get cosine of 0. That's equal to 1. Okay, f of, for example, pi over 4. Cosine of pi. What's up? Someone wanted to say something? F of pi over 3, that's cosine of pi over 3, and that gives us 1/2. And let's just take f of pi over 2. Plug pi over 2 in the function, you get cosine of pi over 2, and that is equal to 0. Okay. And actually, guys, let's utilize the polar grid here for this example. Show you how to use it. All right, so for the sake of this problem, guys, let's say this is 1, this is 0.5, and let's just say this is 1. Okay. Yeah. All right, so this tells you when theta is 0, r is 1. Remember that these are r values, okay? And this is the angle 0. Okay, at that location, r is equal to 1. So you go 1 unit away in that direction from the pole. Here's the pole. Okay, so that point, this point is gonna be on our polar graph. Okay, this tells you when theta is pi over 4. This is theta of pi over 4. R is gonna be root 2 over 2. Again, these are our values. Root 2 over 2 is about what, like a point? Does anybody know? 0.7-ish? Yeah, so here go about 0.7 away from the pole. So we should be right around here. Okay, this distance is root 2 over 2. Okay, when the angle is pi over 3, r is going to be half. So this, again, this is the theta of pi over 3. Okay, on this terminal side, you're gonna go half a unit. So that will put you right here, I believe. Yes, it does. Yeah, so this distance here is 0.5. Okay, and finally, when r is when theta is pi over 2, which is this angle, r is gonna be 0. R is gonna be 0. When r is 0, guys, where are we? Which point has r equal to 0?
Y-axis.
Okay, r equal to 0. Which point in space, which special point has r equal to 0? Yes, the origin, the pole. Yeah, the only point in this whole space where r is 0 is the pole. Okay, so at pi over 2, we're gonna be right on the origin. Okay, this is the pole. All right, so these points are gonna be on the polar graph. If you connect them, if you pick more points and connect them, it forms a semicircle. Okay, yeah, we need more points, of course, more points to make sure that this is a semicircle, but that's what's happening. As the angle gets closer to pi over 2, you see that the angles are getting closer to pi over 2, the value of r gets smaller, the value of r gets close to 0. We have 1, we have 0.7, we have 0.5, and eventually 0, meaning that the distance from the pole to the polar points is getting smaller and smaller. That's what's going on. All right, but again, just plug a bunch of points, polar points, connect them. We are gonna prove later, maybe today or tomorrow, that this is the graph. In fact, this is the graph of a semicircle in the polar coordinate system. That is not a wave. Guys, this is not a wave any longer. I hope you weren't expecting a cosine wave. This is a polar function. Okay, the graph of polar functions are very, very different than the graph of rectangular functions. When you graph cosine theta in the rectangular space, you get a wave. But right here, it gives us a circle, actually. If you do more, if you pick more points, you'll see a full circle. Okay, yeah. But we're gonna discuss this particular function maybe today or tomorrow. Okay, so let me talk about common polar functions that you guys are gonna see a lot. All right, so let's begin with the most simple polar function, r equal to some constant a, where a, assume, is positive. Alexei, I don't know. I have no idea. Are they utilizing a sonar for sonar? Yep, most likely. I'm not sure. I'm not like, I don't know everything, okay? I can look that up. Yeah, but can anyone tell us what this is gonna graph for you? R equal to A. What is this graph gonna generate? They do, okay, cool. A line, guys, AJ said a line. Jose says a circle. Isn't that interesting? I was hoping for someone to say a line. I was really hoping for that. This thing in rectangular space would be a line. If you draw y equal to a, that is a horizontal line, okay? But we are in the polar space. This is something very different. This is actually a circle, okay? What this tells you, this equation, is that r is the distance. The distance from the pole to the polar graph is constant. That's exactly the definition of the circle. The pole to the points on the graph. So we're talking about r is a constant a. This is the definition of the circle centered at the origin. Okay, theta equal to 1 is not a, is actually, yeah, that is a line, AJ. We'll see that also. But if you don't believe this, you can always plug points, you know. Choose values for theta to see what r is. If you choose theta to be 0, r is a. If you choose theta to be pi over 4, r is still a. R is independent of theta. Okay, whatever you want to choose for theta, r is still going to be a. Choose pi over 2, you get r equal to a. Okay, so we'll just, I'll just use the polar grid. So again, let's just say this is a, let's just say, okay. So again, when theta is 0, that's theta of 0. go a units from the origin. When theta is pi over 4, go a units from the origin. So somewhere around here. Okay, so when you just do this for all angles, you're just going to end up with a circle. Okay. Again, for that angle, go a units. For that angle, go a units. For pi over 2, go a units. Go a units in all directions and you get exactly a circle. All right, so r equal to some number in polar form gives you a circle. All right. Isn't that great? The equation of a circle in polar form is a constant. That makes calculation for circles really easy, guys, really easy. If you're in the Cartesian system, you want to do anything that has to do with circle, like area, derivatives, you know, anything calculus, anything calculus that has to do with circle, using calculus 1 methods is very difficult. But now, equation of a circle is a constant, and everything with that is going to be easy.
Professor, real quick, if
Yeah.
R, could you scroll up just a tab?
Yes, I can. So let me just adjust that.
So if A is greater than 0, how do we get negative A? When we're
If-
graphing the entire circle.
Can you repeat that question one more
So,
time?
excuse me, R equals A where A is greater than 0. How come when we're graphing the circle, we have 2 negative A points?
Oh, so, okay, I got you. Right. Yeah, so when theta is equal to pi, okay, if I go a units away from the pole, I end up here, right?
Yeah,
In that direction, go a unit. I guess
should be absolute value then, or?
no, this is just, if this is the y-axis, this is the x-axis. Isn't that just negative a?
Yeah,
I guess it's you're getting confused because I am writing the Cartesian distance. Is that what's going on
I
here?
think so.
Oh yeah, that's what's going on. Okay, I got you here. Let me fix that for you then.
Thank
So
you. It was
this
just a little confusing.
Yeah, this is a0. This is a pi over 2. This is a pi. Does that make sense?
Yeah, it makes perfect sense now. Thanks.
Okay, very good. I was writing that as negative a, thinking of this as the x-axis, that as the y-axis. So again, the circle centered at origin is a constant in polar form. We like constants. You can also, to prove that this is a circle, you could do something else. If you have r equal to a, okay, this is our polar equation. you want to transform this to, like, let's say rectangular equation so that you can identify it. What you do is just square left hand and square right hand. You get r squared equal to a squared. And look at your transformation rules right there. This tells you what r squared is equal to. It's x squared plus y squared. Okay, so left-hand side is x squared plus y squared. Right-hand side is a squared. That's the equation of the circle of radius a, centered at the origin, isn't it? Yeah, if you have a polar equation, you can transform it to rectangular equation if you can. And then, yeah, you're more likely to identify it. That's what we did here. Okay, so let's get the second most common polar equation, and it is r equal to a cosine theta. Okay, this is what I tried to graph a little bit earlier. We graphed r equal to 1 cosine theta, okay? But we want to know what happens if you have, like, let's say cosine theta with some number in front. This a is just a constant number. All right. So to identify this equation, it's definitely not as easy as the last equation. We can't just try to rationalize and say, oh, just because theta is that and a is that, we get this certain shape. What you can do is you can transform this to its Cartesian form, to its rectangular form, by using the transformation rules. Okay, here we know from earlier that x is r cosine theta and y is r sine theta, right? So if we had an r, if we have an r over here, then that would be an x. Okay, so multiply this equation by r. Okay, multiply the left-hand side by r, multiply the right-hand side by r. You get r squared equal to a r cosine theta. All right, yeah. Multiply that by r. This is what you get. R squared, transformation rules tells us that r squared is just x squared plus y squared. Okay, and on the right hand, we have a. And again, r cosine theta is just x. So a times x. All right, now we have the rectangular form of the same equation. X squared plus y squared equal to ax. I'm not sure if you guys can identify this object easily, but this is a circle. This thing is also a circle because we have that x squared plus y squared. It's just that this circle is no longer centered at the origin. This is a circle. It's an x squared plus y squared. This is a circle that is shifted, and I will show you guys tomorrow how to find the center and the radius of the circle, but we are out of time today. See you tomorrow.
Thanks, Robert.
Yes, sir.
Thank you.
Yeah. Hey, Jay, you're gonna guess a line again? Far from that. I know you're kidding. Have a good day.
Thank you, Professor.